Combinatorics, Lecture 16, Partitions and Set Partitions. We start with partitions. Let n be a non-negative integer. Definition: a partition of n is an ordered collection lambda equal to lambda 1, lambda 2, and so on lambda k of positive integers satisfying the following two conditions. First of all, this collection weakly decreases, which means lambda 1 is greater than or equal to lambda 2, lambda 2 is greater than or equal to lambda 3, and so on. And the second condition is that lambda 1 plus lambda 2 plus and so on plus lambda k is equal to n. For example, if n is equal to 0, then we have a unique partition of 0, which is the empty set, the empty collection. Example 2. If n is equal to 1, we have a unique partition which just consists of 1. If n is equal to 2, we have two partitions, 1, 1, and 2. If n is equal to 3, then we have three partitions, 1, 1, 1, 2, 1, and 3. So an individual summand of a partition is called a part, and if some parts repeat, so if you have a repetition I, and so on, k repetitions of a part I, it is usually written I to the power k. Very confusing notation, but it's standard. So for example, the partition 3, 3, 2, 1, 1, 1, 1 of 12 would often be written 3 squared, 2, 1 to the 4th, or even 3 squared, 2 to the power 1, 1 to the power 4. Here is a notation. Lambda is a partition of n, is denoted by this symbol, and the number of different partitions of n is denoted by p of n, and this function p is called the partition function. So that's a function which is defined on all non-negative integers, and it takes value in positive integers. So these partitions are sometimes also called integer partitions. So these are partitions of integers, of positive integers or non-negative integers. The values of the partition function for small n is as follows. There is one partition of 0, one partition of 1, two partitions of 2, three partitions of 3, 5 partitions of 4, 7 partitions of 5, 11 partitions of 6, 15 partitions of 7, and 22 partitions of 8. It is very easy to write the generating function for the partition function p of n. So recall that the generating function is just the sum over all n, p of n times x to the power n. And the claim is that this function can be written as a product over all k greater than or equal to 1, and the factor which corresponds to k is 1 divided by 1 minus x to the power k. Indeed, the coefficient at x to the power n on the right-hand side of this equality, so in this product, equals the number of all possible non-negative integer solutions to the equation y1 plus 2y2 plus 3y3 plus and so on equals to n. And this number is clearly equal to p of n due to the definition of p. y1 tells how many parts are equal to 1, y2 tells how many parts of the partition are equal to 2, y3 tells how many parts of the partition are equal to 3, and so on. So this uniquely describes a partition. Next, let us look at the statement which is called Euler's theorem. Claim: for any non-negative integer n, the number of partitions of n in which all parts are odd equals the number of partitions of n in which all parts are distinct. There is a very nice and short proof of this theorem using generating functions. Similarly to our computation of the generating function for the partition function p, the generating function for the number of partitions of n in which all parts are odd equals the product over all k greater than or equal to 0, 1 divided by 1 minus x to the power 2k plus 1. And similarly, the generating function for the number of partitions of n into which all parts are distinct equals the product over all k greater than or equal to 0, 1 plus x to the power k. So what we need to prove is that the first product is equal to the second product. So the product of 1 plus x to the power k over all k should be equal to the product of 1 divided by 1 minus x to the power 2k plus 1. Let us multiply both sides of this product with the product over all k of 1 minus x to the power k. That's the denominator for the generating function of the partition function. And this is an invertible formal power series because the free term is equal to 1. Let us note that 1 plus x to the power k times 1 minus x to the power k is equal to 1 minus x to the power 2k. So on the left-hand side, each 1 minus x to the power k will hit the corresponding 1 plus x to the power k and create 1 minus x to the power 2k. So we will get the product k from 0 to infinity 1 minus x to the power 2k. That's the left-hand side. And on the right-hand side, the terms with odd powers of x will just cancel, and what remains are terms with the even power of x. And that's exactly the left-hand side which we just computed. This completes the proof. Next, let us talk about Young diagrams. Young diagrams is a nice pictorial way to visualize partitions. So an alternative way to represent partitions is using Young diagrams. The Young diagram of a partition lambda, written in English notation, is a diagram of boxes aligned in the upper left corner, where the top row contains lambda 1 boxes, the next row contains lambda 2 boxes, and so on. So for example, the Young diagram of the partition 5, 4, 2, 2, 1, that's a partition of 14, is the following diagram. We have 5 boxes in the first row, 4 boxes in the second row, 2 boxes in rows 3 and 4, and 1 box in row 5. This is the Young diagram of this partition. So let lambda be a partition of n. The conjugate or transposed partition lambda prime is defined as follows. Lambda j prime is equal to the number of I such that lambda I is greater than or equal to j. And of course for those j for which this entity is non-zero. So for example, if lambda is 3, 2, 2, 1, 1, that's a partition of 9, then lambda prime is 5, 3, 1. Note that this is also a partition of 9, so in fact it's easy to see that lambda prime is a partition of n, if lambda is a partition of n. And the easiest way to see this is to observe that lambda j prime is defined at the height of the j's column of the Young diagram of lambda. And as a consequence, the Young diagram of lambda prime is obtained from the Young diagram of lambda by transposition of the diagram. So if lambda is 3, 2, 2, 1, 1, when we transpose this picture, we will get 5, 3, 1. So this is how it works. This has a very nice application, proposition. For all positive integers n and k, the number of partitions of n with at most k parts coincides with the number of partitions of n in which each part is not greater than k. Proof? In order to prove this claim, we just need to observe that transposition of partitions maps partitions with at most k parts to partitions in which each part is not greater than k. And transposition is clearly a bijection on partitions, and vice versa, transposition maps partitions in which each part is not greater than k to partitions with at most k parts. And this implies this proposition. Some general remarks and comments about partitions. Partitions of n indexed bijectively conjugacy classes of the symmetric group Sn. This means that they play important role in the representation theory of this symmetric group, and I refer to the course representation theory of finite groups for details on that. Via Sn, they are also connected to the representation theory of the general linear group GLN, because the representation theory of GLN and Sn these two series are connected by the so-called true-while duality. And also partitions in general, integer partitions, have many applications to number theory, combinatorics, algebraic geometry, probability, statistical mechanics, computer sciences, and so on. Next, let us talk about set partitions. So let X be a set. Definition: a set partition of X is an unordered collection of non-empty and pairwise disjoint subsets of X, such that X coincides with the union of the subsets in this collection. So for example, if we take the set consisting of 1, 2, and 3, then this set has the following set partitions. The first collection has 3 components, singletons 1, 2, and 3. The second collection has the singleton 1 and the set 2 and 3. The third one is 1, 2, and 3. The fourth one is 1, 3, and 2. And the last one is 1, 2, 3. The whole set as one part. Remark, the only set partition of the empty set is the empty collection. That's a usual convention which we have. And we just see that the set with 3 elements has 5 different set partitions. Let us enumerate set partitions. So let us denote by lambda of n the set of all set partitions of the set 1, 2, and so on n with n elements. Then lambda of 0 consists just of one element, the empty set, the only partition of a set with 0 elements of the empty set. Next, for k between 1 and n, let us denote by lambda n comma k the set of all set partitions of 1, 2, and so on n with exactly k parts. Let us note that lambda of n is the union of this lambda n comma k, where k ranges between 1 and n, and this union is disjoint. Definition: the number Bn, which is defined as the cardinality of lambda of n, the number of set partitions of n, is called the nth Bell number. And another definition: the number Sn, k, which is defined as the cardinality of lambda n, k, is called the Stirling number of the second kind, or Stirling partition number. Since lambda of n is a disjoint union of lambda n, k, we have that Bn is equal to the sum k from 1 to n of Sn, k. That's a direct consequence. Here are some examples. For n equal to 2, we have that lambda of 2 consists of 2 different set partitions. One is 2 singletons 1 and 2, and the second one is the whole set 1, 2 together. So B2 is equal to 2. Also, lambda 2, 1 just contains the set partition of 1, 2 with one part, that's just 1, 2. So S2, 1 is equal to 1. And lambda 2, 2 consists of one set partition of 1, 2, and that set partition has 2 singleton sets, 1 and 2, so S2, 2 is also equal to 1. So for n is equal to 3, we just computed that lambda of 3 has 5 elements. There are 5 set partitions of 1 to 3. So the 1 to 3, 1, 2, 3, 1, 2, 3, 2, 1, 3, and 3, 1, 2. So these are the 5 set partitions of 1 to 3. So B3 is equal to 5. S31 and S33 are equal to 1. There is only one of these partitions with one part and only one with 3 parts. And there are 3 partitions with 2 parts, so S3, 2 is equal to 3. Here is a table of values for the Bell numbers for small n. So Bn is equal to 1 if n is 1. So B2 is 1, B3 is 2, B4 is 5. B5 is 15, and then we have 52, 203, and 877. Theorem: Bell numbers satisfy the following recurrence. For all n greater than or equal to 1, Bn equals the sum over all k from 0 to n minus 1, and then the binomial coefficient n minus 1 choose k times bk. Proof: For each k between 0 and n minus 1, let us denote by lambda of n upper k the set of all set partitions in lambda of n for which the part containing n has exactly k plus 1 elements. Further, for a fixed subset Q in 1, 2, and so on n minus 1 of cardinality k, let us denote by lambda of n upper k comma q the set of all elements in lambda of n upper k for which the part containing n is exactly q union with n. Note that we can choose this q in n minus 1 choose k different ways, which is the same as n minus 1 choose n minus 1 minus k different ways, because it's a subset of 1, 2, and so on n minus 1 of cardinality k. Then lambda of n is a disjoint union of all these lambda of n uppercase, and each lambda of n upper k is a disjoint union of lambda of n upper k comma q's. Okay, given an element xi in lambda of n k comma q, we can remove from xi the part q union with n and get a set partition of the set 1, 2, and so on n minus 1 minus q, and this set has n minus 1 minus k elements. Conversely, given a set partition of the set 1, 2, and so on n minus 1 minus q, we can add to this set partition the part q union with n to get an element of lambda of n upper k comma q. This means that there is a bijection between the set of all set partitions of 1, 2, and so on n minus 1 minus q and the set lambda of n upper k comma q. So the cardinality of lambda of n upper k comma q is equal to the Bell's number with index n minus 1 minus k. But this means that Bn equals the sum over all k from 0 to n minus 1, then the binomial coefficient n minus 1 minus k, and then b n minus 1 minus k. And we can just rewrite it by changing k to the sum over all k from 0 to n minus 1 choose k times bk, which was the claim of our statement. Here is an array which presents the values of Sn, k for small n and k. So if n is equal to 0, it's only S00, 0, which is 1. For 1, it's only S11, 1, which is 1. For n is equal to 2, we have 1 and 1 for k, 1 and 2. And then we have 1, 3, 1, 1, 7, 6, 1, 1, 15, 25, 10, 1, 1, 31, 90, 65, 15, 1. And for n is equal to 7, starting from k is equal to 1, we have 1, 63, 301, 350, 140, 21, and 1. So we have already established a recurrence for Bell numbers. Here is a recurrence for Stirling numbers. For all n greater than or equal to 1, and all k between 1 and n, we have that Sn, k equals S n minus 1 k minus 1 plus k s n minus 1 k. And the initial conditions are that Sn, n is 1 for all n, and Sn, 0 is 0 for all n greater than 0. Proof. Given a set partition xi in lambda n, k, we can consider the part x in xi which contains n. This part is either a singleton or not. If it is a singleton, we can remove it, and then we get a set partition of 1, 2, and so on n minus 1 with k minus 1 parts. Therefore, there are exactly s n minus 1 k minus 1 such possibilities. If the set x is not a singleton, we can remove n from this part x, and then x without n with the rest of xi gives a set partition of the set 1, 2, and so on n minus 1 with k parts. Conversely, given a set partition of 1, 2, and so on n minus 1 with k parts, we can attach n to any of these k parts and obtain a set partition of 1, 2, and so on n with k parts in which the part containing n is not a singleton. Therefore, there are exactly k times s n minus 1, k such possibilities. And if we add the two numbers up, we exactly get the necessary recurrence. And this completes the proof. Finally, let us discuss the exponential generating function for Bell numbers. Theorem: the exponential generating function for Bell numbers is equal to the exponent of x minus 1. Here is a short proof. We know that Bell numbers satisfy the recurrence that Bn plus 1 is equal to the sum k from 0 to n choose k times bk. We have proved this recurrence, and the initial condition is that b0 is 1. Consider the exponential generating function, which we denote by b of x. So b of x is the sum over all n bn times x to the power n divided by n factorial. So we take our recurrence, we multiply it by x to the power n divided by n factorial, and we sum up over all n greater than or equal to 0. So the left-hand side is the sum over all n bn plus 1 x to the power n divided by n factorial, and the right-hand side is the sum over all n, sum over k from 0 to n choose k bk x to the power n divided by n factorial. So if you look at this left-hand side and replace n plus 1 by m, we get the sum over all m from 1 to infinity, bm times x to the power m minus 1 divided by m minus 1 factorial. And that's exactly the derivative of b of x. On the right-hand side, we can interchange the summation. So sum over all n, and then sum over all k from 0 to n choose k bk x to the power n divided by n factorial becomes sum over all k, bk times sum over all n that are greater than or equal to k, and choose k x to the power n divided by n factorial. N choose k times 1 divided by n factorial is just 1 divided by k factorial times n minus k factorial. So we can move x to the power k divided by k factorial out from the second factor, and what is inside is the sum over all m greater than or equal to 0, x to the power m divided by m factorial. But that's exactly the exponent of x. So the second factor can be replaced by x to the power k divided by k factorial, the exponent of x, and so the right-hand side becomes the sum over k, bk times x to the power k divided by k factorial, the exponent of x. But that's exactly the exponent of x times the original generating function b of x. So this means that our generating function satisfies the following first-order ordinary differential equation. b prime is equal to e to the power x times b of x. If we separate the variables, we will get b prime divided by b is equal to e of x, which implies that the natural logarithm of b of x is equal to e to the power x plus c. So b of x is equal to some constant c0 times the exponent of the exponent of x. So since b of 0 is b0 is 1, we find that our constant should be the exponent of minus 1. And this implies that b of x is equal to the exponent of the exponent of x minus 1. Some additional problems and questions at the end. Problem question 1. List all partitions of 6 and 7. Problem question 2. For a fixed m greater than 1, prove that for any non-negative integer n, the number of partitions of n in which all parts are not divisible by n equals the number of partitions of n in which multiplicities of repeating parts are all smaller than m. Problem question 3. Determine the generating function for the number of partitions of n that are self-dual with respect to conjugation. Problem question 4. Prove that b of n equals the sum over all k from 0 to n, 1 divided by k factorial, times the sum over all I from 0 to k, minus 1 to the power k minus I, times k choose I, times I to the power n. And problem question 5. Prove that S n, n minus 1 is equal to n choose 2 for all n greater than or equal to 2. Thank you very much, and see you next time.